in general, how do we find the volume of a sphere with a radius of 4? We should just use the formula, right? What's the formula for the volume of a sphere?
4/3 radius r. Oh yeah, 4/3 r cubed. Oh, pi r cubed.
Pi r cubed. 4/3 pi r cubed. So if our sphere has a radius of 4, this ought to just be 4 cubed is 64 times 4 is 256. So 256 pi over 3. Should be easy enough, right? True?
Yes.
All right, now we're going to do this using integration and make sure we get the exact same value. And I've drawn us a semicircle here, a semicircle that happens to have a radius of 4. And what could I do with just a plain old flat semicircle with a radius of 4? How could I manipulate that and move it around to turn it into a sphere with a radius of 4?
Rotate it around the y-axis.
All right, so if I rotate around the y-axis, that's just going to give me a hemisphere, right? It's going to give me the top half of a sphere. True?
Around the x-axis.
That'll do it. If I rotate it around the x-axis here, so imagine that it's coming out of the screen towards you and then going back inside of your computer screen, back around in 3 dimensions, you're going to end up with a sphere that has a radius of 4. Okay, so effectively, I'm turning this semicircle right into a sphere with a radius of 4. So now the cool thing about a sphere is if I slice it, let's say I slice it right there where I drew that line, and then open it up the faces, what do they look like? What does the face of what I'm on the inside of where I've sliced look like?
Circle.
Circle. What if I slice it right there? Oh, that was hardly in the circle. What if I turn the sphere? What if I slice it right there? What do they look like?
Circle.
Circle. What if I slice it like that? What do they look like?
Also a circle.
Circle. What if I do it perfectly horizontally, which that is not, but pretend that is?
Also circle.
What if I do it perfectly vertically? That one was better.
Still circle.
Still a circle. Oh, man. Okay. These are still circles, right? So that's what we're going to do. We're going to take this 3-dimensional solid that we're thinking about here, this sphere, and slice it perfectly vertically. And we're going to use the same idea that we did with the volume of our cross sections, where we had square cross sections or rectangular or semicircular cross sections, and just think about it that way. Each cross section is a circle, as we just said. So we're going to say cross sections, and we're going to say perpendicular to x-axis are circles. And I'm just specifying that we're going to do a perpendicular to the x-axis because each of those circles then that I get here, right, if I get a little circle here, has a thickness of dx. And so if we're going to use the same idea of finding the volume using cross sections that we were using previously, we're going to have to do it all in terms of x. And so what is the area of this circle? What is the area of that cross section? Pi times the
Radius squared.
Radius squared, because those are circles, right? So we got pi times the radius squared. Well, all we needed to do when we were doing volume with all these things like we just did on the quiz was we took our pi, we took our radius squared, we took our dx, our thickness, multiplied it by that, and then we integrated from the furthest left, which is -4, to the furthest right, which is 4. So we're basically set up exactly the same as we were with all these other problems we've been working on, except we've got an r squared dx, which is a problem. So we got to figure out how to write r in terms of x. Well, what's the equation of this semicircle? That's gonna help us.
Y equals the square root of 16 minus x squared.
Exactly. And why does that help us?
Because we can solve for x.
Well, what's our radius? Our radius is that.
Y.
Yeah. Our radius is y. So our radius is root 16 minus x squared. So what is r squared? R squared is just
16 minus x.
just the 16 minus x squared, exactly. So we have pi times the integral from -4 to 4 of 16 minus x squared dx. And now we should be able to integrate. Pi will stay out in front. The integral of 16 is 16x. The integral of -x squared is -x cubed over 3. And we'll go from -4 to 4. So 16 times 4 is 64, minus 64 thirds, and then minus, and then at -4, it's -64, and a plus 64 thirds. And so 64 and 64 is 128. And then we've got a minus 128 thirds. 128, if we multiply that by 3, ought to be, what, 384? 384 minus 128 ought to be 256. We end up with 256 pi over 3. Exactly the same thing that we got before. Good or no? Any questions on that? You all still there?
Yeah.
We're good or no?
Yes.
Wonderful. Now, people are just keep leaving and leaving and leaving. People keep dropping. All right. So kind of cool that the formula gives us the same thing. Now, let's think for a moment. Let's see if we could do something even cooler than just taking a semicircle with a radius of 4. What if I just said that my semicircle had a radius of r? There's my semicircle with a radius of r. This equation here would be r squared minus x squared. And if we were to revolve that around the x-axis, that would give us a sphere with a radius of r, right? If I revolve that around, we get this really horribly drawn sphere that I've tried to draw here. Would you guys agree with that?
Yep.
Yeah. And so if we were to set this up in exactly the same way as we just set up the last one, we just replace the 16 with r squared, right? And what would we replace the -4 and the 4 with?
Negative r and r.
Negative r and r. So we'd have pi times the integral from -r to r of r squared minus x squared dx. And keeping in mind here that r is just some number, right? It's just the radius. So r squared is a constant. Okay. So when I integrate r squared, what do I get? If I integrate a constant with respect to x, what do you get?
That constant times x.
That constant times x. So r squared x, and then the integral of the x squared is still x cubed over 3. And we're going to evaluate that from -r to r. So we're going to plug -r and r in for x and subtract. And what do we get? We get pi times r cubed minus r cubed over 3 minus -r cubed plus r cubed over 3. And we would find that we have a pi, we'd have a 2r cubed, and we'd have a minus 2/3 r cubed. And 2r cubed is 6r cubed over 3. So 6r cubed over 3 minus 2r cubed over 3 would be 4r cubed over 3. And we'd end up with 4/3 pi r cubed. And you would be astounded and amazed that that is exactly how the formula for the volume of a cube was developed, right? It's just taking this semicircle with a radius of r, revolving it around the x-axis, and integrating a formula for the area of the cross-section times its thickness. Isn't that cool?
Very.
Yeah.
Yes. You've been able to find the volume of a sphere since you were like 6 years old. But this is the first time probably that you ever actually saw why that formula works. It's amazing. Isn't it amazing? The answer is yes, it's amazing. It is amazing and astounding. All right. Now, let's see. Something. Did I say cube?
Yeah, you said cubed.
I said cube?
You said the volume of a cube.
Really? Oh, weird. I meant to say sphere. I don't know. I get distracted at home because like my dog is walking around bleeding all over the place, and then my child is like running around throwing shirts at my head, and like I get distracted. Sorry. I meant to say sphere. I meant sphere. Volume of a sphere. Can't believe I said cube. That's weird.
And you also meant to say that your dog is bleeding?
Yeah, I did mean to say that. Yeah. I meant to say that.
It's okay?
Yeah, she's fine. She's got this like growth on her leg and she keeps chewing it off and then she bleeds all over the place. She's supposed to get it removed, but like my vet didn't have surgery appointments till June. So for the last like 4 weeks, she's just been wearing a cone to stop her from chewing off this giant growth on her leg. It's really fun. They moved her appointment up, so now her appointment's in like the middle of May, so that's good news. So she only has to wear a cone for another month. So she's not currently actually bleeding all over, but she was right before class today. Keeping an eye on her. She's wandering around the house trying to find a place to bleed. It's fun. All right. Yeah, what day was it? Tuesday when I came home from school. Wednesday when I came home from school. I came home to just like blood everywhere all over my floors. That was fun. It's always good. All right, let's continue on. We got a few minutes left here, yeah? We should do some more stuff there. Let's take a look at this. Actually, let's go back a second. Why do we care about any of this? Why do we care about like we revolve this semicircle around? I mean, we got a formula for it already, and we're using these cross sections, right? Well, what's cool about this idea of revolving something around the x-axis and being able to find its volume? All right. Well, let's see. Here's a function. You got a function you like? You like this function?
No.
No? Too bad. Okay. There's f of x. And f of x has some region that is between it and the x-axis, doesn't it? From 0 to a. Would you agree?
Yes.
Yes. Okay. Now, is this region here a regularly shaped region, something we know about, like a sphere or a cone or a pyramid? Or like a triangle or something? No, it's not. But if I were to take this irregularly shaped region and revolve it around the x-axis and pretend that I drew that perfectly, exactly the same, revolved it around the x-axis and sliced it vertically, what would the cross sections look like?
A circle?
An ellipse.
They should be, well, if it's revolved around the x-axis, each cross section should be a circle, right? Each one of these should be a nice, perfect circle. All the circles are going to be different sizes, but we're going to have circles all the way around, from 0 to A. And if the cross sections are circles, the cross sections should just be represented by pi times the radius squared, shouldn't they? And they should just have a thickness of dx. And if I wanted to find the volume of them, I should just be able to, or find the volume of this full solid, I should just be able to integrate from 0 to a pi r squared dx, where r is my function. And so this idea should allow us to take any weird, irregularly shaped region or regularly shaped region, revolve it around the x-axis, and find the exact volume of it, even if it's totally strange looking, like this function was, right? Some sort of weird, demented cone funnel looking thing. We should be able to find its exact volume. And that's the whole idea of what we're going to be doing basically for the rest of this unit, is we're going to be taking weird regions, revolving them around the x-axis or the y-axis or around some random line and finding their volumes. And we're going to use this idea of circular cross sections to find their volumes. That's our goal for the rest of this unit. Sound good? Does that conceptually make sense?
Yeah.
Great. So let's take the function, the square root of cosine x from 0 to pi over 2. And we're going to revolve it around the x-axis and find its volume. So here it is. Here is square root of cosine x. I'm drawing it right there. From 0 to pi over 2. And we're revolving it around the x-axis. So we just get, I don't know what that looks like. It's sort of like the bottom of an acorn or something like that. And we'd like to be able to find the volume. So if I slice it vertically, what do the cross sections look like?
Circles.
These are circular cross sections. Exactly. And that's anytime we revolve, we are effectively going to get circular cross sections. So what is the radius of one of those cross sections? It's the distance from the x-axis to the function, which is y. And so since they're circular cross sections, we want pi r squared, which should be pi times cosine x. They have a thickness of dx, and we'll integrate from 0 to pi over 2. Does that make sense?
Yes.
Everyone feels good about that? So we have pi. What's the integral of cosine?
Sine.
So pi times sine x from 0 to pi over 2. What's the sine of pi over 2?
1,
And the sine of 0?
0.
And so we just end up with pi units cubed as our volume. That's simple. Pretty cool, huh? Take any horrible, awful looking function, revolve it around the x-axis. Should be able to find the volume using this method. Any questions on that? No? All right, let's do another one. So here we have got the function 2 plus x cosine x from -2 to 2. And we're going to revolve it around the x-axis. So what is that going to look like? It's going to look something like this. I don't know, like a flower vase or something like that, yeah? And how much water can I fill this vase with? Well, that would be the volume of it, right? And how will we do that?
By using an integral.
That's right. And our integral is going to have to be done in terms of x, because we're going to slice it vertically. So the thickness of these cross sections will be very, very thin in the x direction. It should be pi times the integral from -2 to 2 of our radius. Well, our radius is just from the x-axis to the function, isn't it? That's y. So it ought to be 2 plus x cosine x squared dx. Does that setup make sense to everybody?
only squared because there's two y's in the radius.
It is squared because remember these are circular cross sections, and the area of it is pi times that radius squared. Does that make sense?
Yeah.
All right, now this integral, even if you were to distribute this out, you get 4 plus 4x cosine x plus x squared cosine squared x squared, or cosine squared x. That's an integral that is a calc 2 integral you won't be able to do. So we're going to use our calculator to approximate this. Now, did we approximate any integrals using calculators during quarter 2?
I believe so. I think we went through like the process of like the line and then the line and then it keeps going until you get a number.
And then it keeps, no, our calculator should be able to find, I don't know what you're saying, but we should be able to find an approximation for this using your calculator. So here's what you're going to do. On your graphing calculator, you all have your graphing calculator by you, I assume, because you were all using it even though you weren't supposed to on the quiz. Right. You're going to hit the math button. Yes, everyone has hit the math button.
Hit the math button.
You're going to go to option 9. Option 9, depending on how old your graphing calculator is, option 9 says one of two things. It might say the integral of, I don't know, it might just be like an integral sign, a to b something. It'll give an integral sign, or it might say f(n) int with a parenthesis, okay, when you hit option 9. Okay. If your graphing calculator is newer, it will give you the integral sign, and you'll probably be able to figure out what to do. You'll type in a -2 as the lower limit, if 2 is the upper limit. You'll type 2 plus x cosine x squared, and then there'll be like a little d at the end with no variable attached to it. You'll type an x in there, and you'll evaluate your integral, and don't forget to multiply it by pi afterwards. So I'm assuming that that is most of you. Yours probably looks like this, most of you. Is that accurate?
Yes.
Okay. And it's very important that you're able to evaluate an integral on your calculator, because if you can't evaluate an integral on your calculator, you will struggle horribly in the calculator section. So you need to be able to do this. So math 9 and then the integral. Do any of you have a calculator that tells you f(n) int when you hit enter? Anybody? Anybody? Nobody? Yes. Okay. So if yours says f(n) int, what you're going to do is you'll have your f(n) int parenthesis. Then you're going to type in your function, 2 plus x cosine x squared. Then you're going to type a comma. Then you're going to type an x. Then you're going to type another comma. Then you're going to type your lower limit, and then another comma, upper limit, and then close your parentheses. And hit enter. And just out of curiosity, what did you guys get for your integral value there?
Multiplied by pi, it's 52.429.
Did you all get 52.429?
Yes.
If you did not get 52.429 and you're convinced that you put it in correctly, go into the mode and make sure your calculator is in radians. Justin, did you get that with your f(n) int one? Because I know you said you had the other, yours came up differently. You did. Perfect. Okay, good. Anybody not able to get 52.429 on their graphing calculator? It's very important that you're able to do that. All right, that is where we are going to stop today. We don't have time to do another problem.